Hello, Assalamu alaikum, and good day to everyone. So, how are you today? I hope you all okay and not affected by this pandemic COVID. So, today we are going to enter chapter 4. So, in this chapter, we learn about digital modulation and transmissions. Just bear in your mind that throughout this chapter, there are might be some slides that I will skip, so just bear in mind. Digital modulations. So I believe you have learned about amplitude modulations, sorry, analog modulations. So the concept is still the same, where modulation is basically the process of merging or combining two type of signals, which are information signal and carrier signals. So in order for the information signal to be transmitted transmission from transmitter to receiver, they need to be carried out by the carrier. So modulation is the process of combining or merging uh, the two signals, the information signals and the carrier signals. So the concept is same goes to digital modulation. So digital modulation is the transmittal of digitally modulated analog signals between two or more points in a communication system. So sometimes digital modulation is also called as digital radio. For the conventional modulations, we have amplitude modulations, we have frequency modulation, and we also have phase modulations. So, but what differentiate between digital modulations and analog modulations? So basically, uh, is what make them different is the nature of the modulation signals. So I would like to highlight this: the nature of the modulating signals. So basically, modulations, we need both analog and digital modulation system use analog carriers to transport the information through the system. However, with analog modulation system, the information signal is also analog, whereas with digital modulation, the information signal is digital, which could be computer-generated data or digitally encoded analog signals. So it shows that the difference between digital modulations and the analog modulation is the information signals. In analog modulations, so the information signal is analog, but in digital modulation, the information signal is in digital module is in digital. Okay. Uh, as I described in the previous slides, in analog modulations, we have amplitude modulations, AM, we have frequency modulations, FM, and we also have phase modulations. The concept also apply in digital modulations, where we have amplitude shift keying or ASK, we have frequency shift keying FSK, and we also have phase shift keying, which is PSK. So these digital modulations we will discuss later in this chapter. Digital modulation is suited for any communication systems, include cable and wireless systems, and the application also can cover for low-speed data, high-speed data, digital microwave, or any satellite communication system, and also cellular telephone, personal communication systems, and others. The following slide will show you the diagram of the digital modulation. This slide shows a diagram of our digital radio systems. So in this diagram, we have two sides, the transmitter side and the receiver side. So at the transmitter side, we have input data. Input data is the data that we want to transmit to the receiver. So at the input data, we have clock here. So what is the function of clock? Normally clock is used to control the sequence of the data to be given to the system. So clock is used to control the input data to the system. Macam kita nak masuk sesuatu dewan, kalau kita ramai sangat, so kita kena beratur. So di pintu masuk itu akan ada proses untuk control orang untuk masuk ke dalam dewan. So the function same goes to clock. Okay, so it control the sequence of the input data to the systems. So before the data need to be modulated, so it will go to the precoder side. Then we have here the analog carrier, the carrier that function to carry the input data. So it will stay at the buffer before it goes to the modulator process. Then at the modulator process, the carrier will be combined with the input with the data. So after the modulation process, the modulated signal will be filtered. BPF is band pass filter. Normally, in this process, the unnecessary signals such as noise will be extinguished or filtered before it will be transmitted. And then after the band pass filtering process, so the signal will be amplified before it will be transmitted to the receiver. So this is the medium, the transmission media. So the transmission media, whether it is wired or wireless. So during the transmission process, normally there will be noise that will interfere the transmitting signal. Okay, so at the receiver side, we have band pass filter again. After the receiver receives the transmitted signal, so it will filter to eliminate the unnecessary signals such as noise. So function at the band pass filter at this side is same as the function of band pass filter at the transmitter sides. So after the filtering process, the filtered signal will be amplified, and then it goes to the demulator and decoder. So this process will divide or separate between the carrier and the transmit and the data. So and then after this process, we have the data that supposedly same as the input data here. So this is the basic the explanation of this basic digital radio system. In digital modulation, there are some terms that you need to understand. First is information capacity, bits, bit rate, and M-array encoding. So first, what is information capacity? Information capacity is a measure of how much information can be propagated through a communication system and is a function of bandwidth and transmission times. So information capacity ini adalah satu pengukuran untuk mengukur sebanyak mana maklumat digital boleh dihantar melalui satu communication system, and is a function of bandwidth and transmission time. Maksudnya bila kita menyatakan tentang information capacity, ia berkait juga dengan bandwidth dan juga transmission time. So information capacity represents the number of independent symbols that can be carried out through a system in a given unit of time. So information capacity juga melambangkan number of symbols ataupun data. Symbols here means the digital data. So normally for the symbol in digital communication, it represents information is the binary digit or bit. So in digital communication systems, simbol normally adalah daripada binary digit, iaitu 01. So bit ni dengan kata lain, ia adalah penjodoh bilangan untuk maklumat digital. Contohnya kalau penjodoh bilangan untuk rumah adalah sebuah rumah, kereta sebiji kereta, dan untuk digital data, sebenarnya kita penjodoh bilangan adalah bit. Berapa data awak ada? Saya ada 30 kilobit data. Okay, so and then normally it's often convenient to express the information capacity of a system as a bit rate. Okay, so untuk information capacity normally dia akan express in terms of bit rate. Bit rate tu adalah simply bit per second. Okay, saya rasa many of you have heard about these terms, bit per second, meaning that how much data can be transmitted for a 1 second duration. So normally we call it bit rate, bit per second. So this is the formula how to calculate the information capacity. So this when we look at this formula, it involves the bandwidth and the signal to noise power ratio, or SNR. Okay, so information capacity I equal 3.32 times bandwidth and the log of 1 plus SNR. So this is the example that explain this formula. For a standard telephone circuit with a signal to noise ratio of 1000 or 30 dB and a bandwidth of 2.7 kHz, information capacity is so we plug in the value from this example to this formula. So please bear in your mind that SNR here need to be use the unitless value, not the 30 dB but 1000. So next is M-array encoding. M-array is a term derived from a word binary, so it's derived from the word binary. M simply represents a digit that corresponds to the number of conditions, labels, or combination possibles for a given number of binary variables. So array comes from word binary, and M actually represents the combinations, how many combinations can be made from the given bits. So it's a long expression here. So basic in sum, basically M array is something that how many combination can be made from the given bits. So this is the formula of how to define number of combination from given bits. So the formula is 2 to the power of n equal m. For example, n is 2, so the given bits is 2. So how many combination can be made from 2 bits? So the answer is 4. So we go to the example next. So this is the example of M-array encoding. With 1 bit, only 2 conditions are possible. So we know that in binary number, we have only 2 numbers which are 0 or 1. So for 1 bit, the combination whether it is 0 or 1. So there is 2 combination can be made from 1 bit. Okay, from let's say this is 1 bit, so whether it is 0 or it is 1. Then for 2 bits, there are 4 conditions are possible to be made. Okay, so let's say this is for 2 bits, so the combination can be made from 2 bits are 0 0 0 1 1 0 and 1 1. So total up is 4 combination from 2 bits. Okay, this is let's say this is 2 bits. Okay, so how about 3 bits? So for 3 bits, the combination can be made from 3 bits is 8. Okay, 3 bits. let's do this together. So from 3 bits we have 0 0 0, we have 0 0 1, 0 1 0, 1 0 0, and so on until 8 condition. Okay, maybe you can do it by yourself. Next is minimum bandwidth. So according to Nike's, binary digital signal can be propagated through an ideal noiseless transmission medium at a rate equal to 2 times that the bandwidth of the medium. So it means that the signal, how much signal can be transmitted to a given medium. So it is 2 times uh, the bandwidth of the medium. So for example, um, a standard telephone circuit has a bandwidth of approximately 2700 Hz, which has the capacity to propagate 5400 bit per second through it. So meaning that the uh, the bandwidth of the medium is 2700, but the capacity to transmit the signal through the medium is 2 times of the uh, given bandwidth of the medium, which is 5400 bit per second. Um, Amplitude shifting, as mentioned in the early chapter, saya ada menyatakan bahawa sama juga seperti analog modulation, di mana modulation ada modulation yang based on the amplitude, ada modulation yang based kepada frekuensi, dan juga ada modulation yang based kepada phase. So kalau di analog modulation kita ada AM amplitude modulation, kita ada FM frequency modulation, dan kita ada phase modulation. So sama juga dengan digital modulation, kita ada modulation yang based on the amplitude. In digital modulation we call it amplitude shift keying, or ASK. So basically this is the formula for the carrier, and this is the result of the result of the formula when it goes to modulation, which is based on the amplitude, which we call it amplitude shift keying. So this is the formula for the amplitude shift keying. So what we can see here, the value of the amplitude shift keying is basically based on the VM. VM is the amplitude of the digital signals. Okay, so for the binary digital signals, when it is +1 for logic 1 and -1 for logic 0. So this is the formula for the amplitude shift keying. When the digital signals is 1, or whether the digital signal is 0. So the first is when the logic 1 means when the digital signals is 1. So this is the amplitude shift keying. So when it is 0, so the result is 0. So we can see clearly in the following example. So this is the example of the amplitude shift keying. So we can see here, this is the digital signals. We have 1 0 1 0. So this is the output of the amplitude shift keying. So we can see here that when it is 1, that is the amplitude in the carrier, meaning that there is a signal here. So when it is 0, the amplitude will be 0, and meaning that there is no signal here. And again, when it is 1, there is a signal in the carrier. So we can see the amplitude shows in this output of the amplitude shift keying, which is we can see there is a wave here, meaning that there is the amplitude. And again, when it is 0, so there is no amplitude, so there is no signal here. So this is another full example of the amplitude shifting. So here we have the input signal, which is the digital signals, and we have carrier signals, and this is the output of the modulation, which is amplitude shifting. So we can see here when there is amplitude, or there is one in the digital signals, so we can see there is a signal here shows amplitude of the carrier exists in the output. So when it is 0, so there is no signal here. So when it is 1 1, so this is 1, this is 1, so the output will show the amplitude of the carrier, okay, and so on. And also this one reflected by this signal. So I think it's easy to understand about amplitude shifting. So next is frequency shifting, which is the digital modulation, which is based on the frequency. So as you can see here, this is the formula for the frequency shifting, which is VFSK. So kalau dilihat kepada formula ini, bahagian yang terkesan ataupun yang affected adalah ruangan ini. Yang ini, okay. So kalau dilihat, if you see this part, so as you can see here, this is the input binary input modulating signal. So kalau dilihat sini, bermaksud jika frekuensi ini berubah, maka the output of the signal, the frequency will change. So kalau ada apa perubahan di sini, bermaksud frekuensinya akan berubah. So kalau kita lihat di sini, perubahan itu adalah disebabkan oleh VM ni. VM ni adalah the amplitude of the binary input. So so as we know, binary only has two amplitude, which is 1 or 0. Okay, this 1, this is 0. So since it only has two value, whether it is 0 or 1, so this whole frequency will be based on the amplitude of the binary. Okay, jadi output of the frequency ataupun frequency output untuk FSK ni depends on the input of the binary logic. So as I mentioned, we have only two logic, which is 0 or 1 for binary. So the output of frequency depends on this, whether it is 0 or 1. So if the input is 0, so the output frequency will be Fs, and if the input is 1, so the output frequency will be the frequency of Fm. So Fm is mark frequency and Fs is space frequency. So if you can see here, this is the output of the FSK, which is based on the input of the binary. So when the input binary is 0, so the output frequency will be Fs, which is the space frequency. While if the input binary is 1, the output frequency for the FSK will be the frequency of mark frequency. So and so on. So this is another example for the FSK. So this is the input, the binary input, which is we have here 0, 1, 0, 1, and 0. So if you see the output of the FSK, so depends on the input, the frequency of the input, the frequency of the output depends on the binary input. So for example, this is 0, so the output will be this frequency, which is space frequency, and this is 1, so the output frequency will be this frequency. So when you look at this output signal, so there is a different frequency between this and this signal and these signals. So the frequency is different based on the input, whether it is 1 or whether it is 0. Kalau dilihat pada awal slide for frequency shift keying, I think you found this symbol delta F. So what is delta F, also known as frequency deviation? So what is frequency deviation? Is the difference frequency between Mach frequency and the space frequency, and then divided by 2. So data frequency also can be used to identify the minimum bandwidth. So this is the formula to define minimum bandwidth based on the given frequency deviation value, and also the value of the input bit rate, FB. So B is the minimum bandwidth, also known as minimum Nyquist bandwidth. So this is an example question for frequency shift keying. Determine A, the peak frequency deviation, B, minimum bandwidth with frequency of with Mach frequency of 49k Hertz and space frequency for 51 kilohertz, and given bit rate is 2 kilobit per second. So it's a simple example. So the important things is how you extract the value and then plug it into the formula. So for the delta, for the frequency deviations, so the answer is 1 kilohertz, while the the minimum Nyquist bandwidth is 6 kilohertz. So next is phase shift keying. Untuk amplitude, untuk phase shift keying dalam digital modulation, the output changes will be based on the phase. So kalau the changes state for the input 0, 1 kepada 0 ataupun 0 kepada 1, perbezaan ni akan dilihat dari segi output carrier-nya sama ada in phase ataupun fasa phase sebaliknya. Ini kita akan lihat contoh dengan lebih jelas. So dalam contoh ini kita lihat kita ada input binary dan juga output daripada phase shift keying ini. So jika input dia adalah 1, maka output carrier dia adalah dalam phase, in phase. Okay, in phase. So kalau dia punya input adalah 0, maka dia punya output dia adalah dalam sudut 180, not in phase lah. So begitu juga seterusnya. Jadi bila kita lihat sini, perbezaan ini, perbezaan output bergantung kepada input sama ada dia 1 ataupun 0. So perbezaan ini akan dilihat dari segi phase nya akan berubah. Kalau dia 1 maka in phase, kalau dia kosong, maka dia not in phase. Untuk kes ni adalah 180 dan juga seterusnya. Ini adalah contoh lain untuk phase shift keying. Kalau kita lihat, kita ada input binary. So kalau dilihat kepada output ni, so changes yang berlaku daripada 1 kepada 0, maka kita akan lihat di sini dia punya perubahan fasa. Untuk contoh ini pula, so disebabkan perubahan fasa daripada 0 ke 1, maka kita akan dapat lihat perubahannya di sini. Dan juga untuk kes ini, daripada 0 ke 1 kepada 0, maka kita akan dapat lihat perubahan fasa di sini. Daripada fasa in phase iaitu 0 kepada fasa non in phase iaitu 180 darjah.